Imagine you're working on the sequel to a big PC VR game, like the original Asgard's Wrath, and it needs to run on the Quest 2. So you're already going from a big PC hardware to a mobile headset. Would you add open worlds? Now, as a cynical engineer, I was skeptical, but Sanzaru rallied behind that vision and decided, let's try it. I'm Dan Halpern, and I'm an engineer at Sanzaru Games. In my segment, I will go over some techniques we use to optimize CPU utilization at scale. Then my colleague Nick Kitten will come up to talk about the render side, and we'll do Q&A at the end. This is Sanzaru Games. Making big games requires a big team, and optimizing at this scale was a massive team effort from all these people and more. Achieving from the design and art teams that actually built these worlds to the production and tools teams that kept the studio running, everybody played a part. Sanzaru has been making VR games since the Oculus Rift, and console games long before that. We joined Meta in 2020 as part of the Oculus Studios group, and last December, we released the subject of this talk, Asgard's Wrath 2. We shipped with Unreal Engine 4.27, and a lot of this should carry over to Unreal Engine 5 as well, but it's worth noting that Unreal Engine 5 also has a lot of new tools for large worlds. Our frame rate target landed at 72 frames per second on the Quest 2 and 90 on the Quest 3, and that's without asynchronous space warp. We decided not to use asynchronous space warp because we were worried about artifacts. And it sounds like the asynchronous space warp team has come a long way since then in reducing artifacts, so that may be more viable today. In terms of profilers, we mostly used Insights for CPU, that's Unreal's built-in profiler, and then we used RenderDoc for GPU. When you see profiles on my slides, those are going to be from Insights. So how big are these worlds? These fly-throughs were recorded on PC by our incredible environment art team, and big thank you to everybody involved in making those. They do a great job of capturing a sense of scale that is hard to capture in playthroughs because it takes so long to move through these worlds, even when mounted. This is the Nile Delta region. And this is our largest area, the Forbidden Desert. Now, we did chop up some of these larger levels towards the end of development into a few chunks, and that's mostly because we were running out of memory. Nevertheless, these worlds are still very large, and there will be some gameplay footage shown later that still sort of shows you, what made it into the final game. So most open world games rely heavily on streaming, and we're no exception, but we took a more conservative approach. Our goals for streaming were to reduce object count. We wanted to avoid death by 1,000 cut situations, and to support overlapping content. So an example of overlapping content is if you might encounter like an encampment at one point in the game and come back to the same area. Maybe there's just wildlife there. Another time, we also wanted to be able to continue to patch in even more content after we release. So we wanted to be able to patch that stuff in without bloating the game. We also needed to keep memory and CPU within budget and limit the number of expensive objects that we had active at a time. So we also had some restrictions to contend with. We relied heavily on pre-computed lighting, and as a result, we had to avoid streaming large chunks of the world if they needed to affect lighting. So that was most of the environment. Also, the lighting data itself was monolithic, so all of the lighting for the entire level was all kind of stored in one chunk of data, and if we needed to switch that, it would cause pretty massive hitches. So we had to do tricks like fade the screen out, switch lighting, fade back in again, that sort of thing. File I/O never really became a bottleneck, nor did the decompress. Those happened on other threads, and they were pretty seamless, actually. However, Vulkan allocations did show up on the render thread that were causing some substantial hitches when we streamed in large amounts of render data. So that was kind of our bottleneck and the limiting factor in how much we could stream at a time. The solution we came up with was to load the environment up front and only stream dynamic elements. So the streaming system and workflow were pretty simple. Design would build gameplay in streaming levels, and then they would place proxies in the world where they wanted this content to stream in. They would set things like the streaming ranges they wanted and priority versus other encounters, an approximate cost. So we sort of just estimated that, and then we tuned it up and down depending on whether we were hitting frame rate targets or not. And a few other properties, progression requirements, that sort of thing. That way you could have an encounter that only came in if a quest was active, or so on. So it's a really simple system compared to most streaming systems in most open world games. But it worked really well on this device. It was very cheap. It was stable, which was important for a team our size. And often optimizing is really about distilling complexity. By considering the workflows of the larger team and empowering everybody to chip in and contribute to the optimization efforts at the end of the project, it really helped us get these large worlds into frame rate. Now, you might be wondering, if we didn't stream the environment, how did we make that performant? And Nick's going to cover a lot of that in his segment. But one aspect I do want to touch on is our occlusion culling system, which we called player spaces. The way it worked is we would divide the world into these large areas or player spaces, and each one would just keep track of like which other area or player space was visible from that area. So when you were in one of these areas, only the areas in that list would render and update, and nothing else would. That was a great first line of defense. It really like reduced the number of stuff, the amount of things that we needed to deal with. However, because our open worlds had long sight lines and the areas were so large, if you could even see into an area from quite a distance away, everything in that large area would be updating. So we used other techniques as well, from distance-based culling to some very customized algorithms to get things updating performantly, and also just to make our algorithms that needed to do searches across a large number of objects performant. So one technique that we used in a bunch of cases that I want to share with you is actually a combination of two that you might already be familiar with. The first is called load balancing, and in the general sense, load balancing is distributing work over a set of resources. But in this case, I'm really referring to distributing CPU load over multiple frames in a simulation. So for example, let's say you had 500 objects and they're all updating every frame. If that was costing too much, you needed to reduce it by a lot, you could update, say, 10 per frame, and that's 50 times as efficient. But of course, it also comes with 50 frames of latency. So depending on your use case, that might or might not be a problem. The other technique is a term borrowed from physics, broad phase. A lot of you may be familiar with that in physics context. It's pretty much building a smaller list of objects that pass an inexpensive validation to make the more expensive algorithm or narrow phase cheaper. So in a physics simulation, that might look like you might do a bounding sphere test, just kind of like, is there any chance these two objects could be colliding at all before you get into the expensive, convex hulls or mesh collision or whatever. So that's how it's traditionally done in a physics sim. When you combine these two together, you get what we call a load balanced broad phase. And it kind of works the same way as a regular broad phase, where it's collecting all the objects that are relevant to a situation. But in this case, it's distributing the work of collection and validation over multiple frames. So that means the contents of the list are latent. They might, they might not be completely validated yet. So what's interesting about this, though, is that we found that we could usually compensate for that latency. So to use an example you're already familiar with, streaming encounters, we sometimes had hundreds of streaming encounters in a level. And we needed to figure out what are the best encounters to stream in. So we used a load balanced broad phase to just kind of keep a running list of the encounters that were just right in your immediate vicinity that also sort of passed all the validation, things like progression requirements, that sort of thing. And that did come with some latency, but when latency became a problem, we were able to pad the distance that we were searching for, in this case, a little bit beyond the streaming radius, to ensure that those encounters were already in the list by the time it was needed. And by performing the check in the narrow phase again, we were able to sort of make it perfectly accurate in terms of the validation, but also perform it in the sense that we weren't doing these checks on hundreds of encounters. Multi-threading is another great way to improve performance, but it can be expensive from a development standpoint. New threaded systems can easily lead to stability issues that can slow down the entire team. And with a team our size, we did not want to risk that in a lot of cases. So we did build some custom solutions where it made sense, but we mostly focused on the tried and true low-hanging fruit, such as Unreal's already threaded systems. And that really saved the entire team a bunch of time just because we didn't have stability issues related to threaded execution. So animation is an example of this. It has a threaded update right out of the box in Unreal. And I'm not going to go into great detail on this because there's tons of documents out there already on it. But my advice with any threaded system is to profile it on a fairly regular basis and make sure that it's actually threaded as you expect it to be, and make sure that the thread you're trying to remove work from, which was for us usually the game thread, to make sure that thread isn't stalling. So this profile on screen shows the animation update for Sabira the Panther split between the game thread and worker thread running in parallel. And this split was pretty typical for us, around 40–45% of the total animation CPU cost. We did find that it varied a bit. So for example, the game thread utilization tended to go up if there was a high bone count. And the worker thread CPU utilization tended to go up if there was a high animation graph complexity. So your mileage may vary, but you can see that there's pretty good gains to be had here. In Asgard's Wrath 2, our collision complexity was very high. Terrain and environment meshes tended to be large to reduce draw calls, and often thousands of collision triangles were the result of that. So overlaps were prohibitively expensive, and we pretty much just avoided using those entirely. We did use collision traces, but we were able to replace some of them with navigation traces, which was a lot cheaper, so tracing along the nav mesh. And then for other things, we were able to offload those into the physics simulation, which was running on another thread. So for example, weapon collision with the environment, we actually made those part of the physics simulation so that we would get our contact points from those instead of a more expensive trace or sweep. If you take advantage of threaded physics like that, I do recommend loading up the during physics tick group, because what will happen otherwise is if the physics simulation takes longer than the during physics tick group to update, you'll get a stall waiting for the physics simulation to complete. So by moving work onto that tick group, you can avoid the stall and actually have your thread running, chugging along smoothly. Most games running on mobile hardware load a static nav mesh, but that did not scale to worlds as big as ours. So we needed threaded nav mesh generation, dynamic generation at runtime, and that's extremely expensive. We also had lots of dynamic elements like moving platforms and puzzle elements, so we needed it for a bunch of reasons. But the cost also, not only is it prohibitively expensive on mobile hardware, but it's also, it kind of scales with collision complexity, and as mentioned, our collision complexity was super high. So So it ended up being so expensive that not only did we have to push all the work onto another thread, but we also had to throttle the update to limit how much it was building each frame, and just to prevent completely saturating that core. There was a lot involved in performance at this scale, and what I presented were just a few pieces of that puzzle. I'm going to pass it to Nick now to cover the render side.
Hi, I'm Nick Kitten, a senior graphics engineer and pixel wrangler, and I'll be covering the graphics side of our optimization efforts. That will include the adjustments we had to make to fit the original Asgard's Wrath's realistic aesthetic on a mobile device, the tools we used, both broad and precise, to locate the cause of performance problems, and how we closed the final gap to reach the finish line. Starting with the move from PC to Quest for the sequel to Asgard's Wrath, we had to reevaluate a few key systems that wouldn't run on mobile. And going from a package that was over 130 gigabytes to one under 30 felt like trying to stuff the genie back in the bottle. First, a note on our philosophy. There were many times when artists asked if they could use a particular built-in Unreal feature to improve the look of the game. And although my instinct was often that it wouldn't run on mobile hardware, my reply would instead be, try it and let me know if it blows up. As a result, many bosses were lit with dynamic point lights in a designated lighting channel, when the standing policy was to use static lighting exclusively. However, our artists didn't need an invitation to max out draw calls. That happened naturally. And the hardware occlusion queries we relied on heavily for fine-grained culling on PC proved too slow on Quest. We switched to using software occlusion, which required additional artist time, had unintuitive behavior, and wasn't as effective at culling. However, it did still have an important advantage over hardware queries. It didn't add to GPU time when we were already render-bound. Compared to another Unreal culling system, pre-computed visibility, it didn't require significant extra storage or memory, and it could handle dynamic occluders and occludees, which was great when some of our most common occluders were doors. A frequent way to reduce draw calls on PC in Unreal is to combine distant meshes with different materials into hierarchical levels of details, or HLODs, using material flattening, which resamples a uniform set of material parameters into a new texture using a unique UV unwrapping. This is wasteful of storage on a resource-constrained device for two reasons. One, any textures used by meshes in HLODs must now effectively be stored twice, once in the source mesh and once in its resampled auto-generated version for the HLOD, even if the HLOD's texture resolution is lower. And two, all the hard work environment artists put into reusing UVs across different parts of the mesh get discarded because of the unique UV unwrapping. Material flattening can't make any assumptions about how the textures are used in the general case, so it ends up having to do a very conservative parameterization that wastes textile detail. Textures also take the most memory of any render assets in our game. Our solution to this problem was to combine textures for different meshes from the start using trim sheets and texture atlases. That way, many different meshes could have just their geometry trivially combined to create HLODs because they would already be using the same materials and textures. In a modern PC renderer, you can go bindless and skip the atlasing, but we heard from other studios building their own engines that that path was still unusably slow on Quest. Speaking of reducing texture bandwidth, ASTC is a great texture format, and we reduced the compression quality on many texture groups with small reductions in fidelity. For reflection captures and some UI textures, we switched from uncompressed to compressed formats. To improve artist workflow, we also modified the normal map identification stage in the engine to change texture import settings automatically based on detected naming conventions. which is easier to do in UE5 using the new interchange framework. We made the mask textures, which held emissiveness, roughness, and metalness, half the dimensions of albedo and normal textures. Finally, if shader compilation during gameplay was annoying on PC, the long hitches felt like a death sentence on Quest. We had QA capture pipeline state objects, or PSOs, regularly during their full game playthroughs to maintain up-to-date entries. Oculus's GitHub branch of Unreal includes helpful fixes for PSO caching that haven't made it back to Epic's mainline as of 5.4. Now I'll talk about the tools we use to diagnose performance problems. I think it's helpful to divide them into two broad categories, which I'll call the sledgehammers and the scalpels. Our sledgehammers were blunt instruments, fast and easy to use without requiring a wealth of technical knowledge, and they knocked out large swaths of potential causes in one fell swoop. Our scalpels were detailed and precise, but typically only used by a few technical individuals. We found investing in sledgehammers first yielded the highest returns because they empowered the whole team to diagnose performance problems themselves, which kept rendering engineers from becoming a bottleneck. Our first group of sledgehammers was a series of toggles powered by console commands, which would show broad stats, disable large systems, or make global configuration changes. We had a custom in-game debug menu from which you could run them with a few button presses, since it needed to be as easily accessible as possible. Every extra barrier to entry would hurt developer adoption. To mitigate noise when running A/B tests, I added a profiling pause debug menu option, which reduced the game simulation speed to a crawl and disabled head tracking to keep the scene steady. Here are a few of the toggles we found most useful. Unreal's show flags were excellent for disabling particular kinds of meshes and rendering systems. I've seen bugs with invisible UI where I could disable basically the entire level, showing an empty black screen, and the game would still be out of frame rate. I also preferred disabling systems before looking at aggregate timers, because doing so can uncover hidden secondary costs. For example, the time spent by the compositor copying stereo layers to the display, which happens outside the game. As an aside, for console commands in general, although we tied the most popular ones to in-game menus or button combinations, when I found myself wanting to use an uncommon console command on a Quest packaged build, I preferred to use the device output log in the editor, which gave me autocomplete and immediate log feedback on whether the command was successful. Again, it was also the user-friendly option I would recommend to artists and designers over ADB and PowerShell. We used the OVR metrics tool for setting art budgets because its measurements factored in the variable effects of the tiled renderer, which Unreal did not. There are several versions floating around, but to get the most recent one, install it from the App Store. We found the most useful metric to be a composite. Multiplying the fill rate by the average instructions per fragment yields a measure of total fragment instructions. This was more flexible than simply limiting shader complexity on its own, because puzzle rooms had lots of overdraw, but simple shaders, while boss battles favored complex character shaders, but simple scenes. Finally, we had two kinds of automated performance monitoring. One ran nightly and would iterate through a set of predefined locations in the game, getting high-level stats like memory usage, game thread milliseconds, and render thread milliseconds that we graphed over time. By capturing from stable locations without user input, it allowed tracking down performance regressions more easily. The other automated monitoring came from analytics, where we would send those same stats, plus the player's current location, directly from the game once every 10 seconds, but only on developer builds. By keeping a dashboard with a list of levels sorted by average frame time, we could easily prioritize our optimization efforts. It would be easy to add a bunch of extra fields to this data and turn the tool into a scalpel, but most of the value was gleaned from simple smoke tests, like preventing out-of-memory crashes. Moving on to scalpels, these were our debuggers and instrumented profilers. The most efficient workhorse for me was RenderDoc, which is a single-frame GPU debugger. For detailed setup and usage instructions, there's an hour-long Connect talk on RenderDoc from 2018 that still largely applies today. One thing that has changed is that Meta publicly released their own fork of RenderDoc, which I highly recommend for getting accurate timing information. Vanilla RenderDoc's performance counters don't take the mobile tiled GPU architecture into account, but the Meta fork can show you timings broken down by tile along with a heat map. You can find a couple blog posts on the added functionality if you search for RenderDoc Meta fork. My favorite underappreciated feature of RenderDoc was the ability to edit shaders in the frame capture, see the visual results, and remeasure performance after those changes. When modifying shaders, the iteration loop was lengthy to change a shader file or material graph, make a build, and then observe results on the headset. Since RenderDoc actually ran the frame capture on the headset, modifying the shader in the capture itself gave me accurate results without all the waiting. Plus, the Meta fork provided detailed stats on the shader's final driver-level instruction counts, occupancy, and register usage, with counters direct from the GPU manufacturer. It's also worth noting that editing shaders in a capture sped up iteration time even for look development on PC in the editor, since modifying any base shader file could cause thousands of derived materials to recompile. Checking shaders in pipeline state in a capture was especially important to verify that the Unreal features being used in our scene were features we wanted. In one case, we saw a dramatic spike in frame times after artists began using vertex fog in their levels. RenderDoc investigation revealed that sky atmosphere was enabled, a sophisticated feature that takes the curvature of the Earth into account. And that one checkbox cost us 8 milliseconds in our levels. In another case, a Vulkan-specific engine bug treated all our bilinear texture samplers as anisotropic. Finally, we used Unreal Insights to check render thread behavior over long periods of time. Especially for brief hitches, it could be difficult to get a single frame RenderDoc capture when the problem was happening. And even GPU-bound frames would often have their workload reflected in the render thread, such as an excess of particle emitters causing too much overdraw, or many GPU-skinned character meshes uploading their bone matrices from the CPU. There are several Unreal Fest presentations on using Insights, so I won't go into detail here. Our biggest wins came from stripping unused system overhead on the render thread. For example, we used a custom drop shadow system in lieu of expensive cascaded shadow maps, but we repurposed existing show flags and primitive properties to control them. Imagine my surprise when I found 3 milliseconds being spent initializing dynamic shadows for hundreds of completely static point lights. Fixing this was the coding equivalent of unchecking a box, and there were similar cases for post-processing passes. Another big source of rendering hitches came from heavy content. For example, uploading cube maps stored in uncompressed HDR format. RenderDoc didn't always catch these issues. If a much higher MIP was always used and the object was small on screen, the draw call itself might not end up being that expensive. Dan added some extra data to the tracing markers to make tracking down these problems easier, since Unreal stripped asset info from render resources like textures and vertex buffers at the lowest levels. Next, I'll cover some of the specific choices we made to go from running at all on mobile to running in frame rate. First, we found that Asgard's RAS art style used fancy pixel shaders, large textures, or both to achieve organic detail. And both approaches make pixels expensive. Realistic games in a more industrial setting can simplify further, but there was no getting past it for us. It took multiple avenues to limit our pixel costs. Our first content compromise was to limit the material complexity of the objects covering the most screen space, namely terrain and the sky. While we relaxed this restriction somewhat on the more powerful Quest 3, for the most part, terrain and props would sample a single albedo texture, use static light and shadow maps, and not modify UVs at all. Our sky domes were similarly simple, no cube maps needed. A smaller group of set pieces added a normal map, and even fewer added emissive roughness and metalness packed into a single texture. We also made several stripped down custom shader models, including one that used dynamic branching on metalness to further cut down on pixel cost in the general case without adding draw calls. In more complex cases, we fell back on the default lit shading model. In some cases, like this terrain with small bits of emissive animation, what was originally authored as a single material was better split into two separate pieces to minimize the expensive pixels. Rather than using cascaded shadow maps, or even the built-in modulated shadows, we made our own system, which toggled between modulated drop shadows and blob shadows, closer to instance decals in functionality than true shadow maps. At the very end of the project, when we were still out of frame rate in a few boss battles on the Quest 2, we enabled dynamic fixed foveated rendering as the big red emergency button to cut down pixel cost even further when necessary, at the cost of some image quality. After bringing down pixel cost, the next highest priority was reducing the number of draw calls. Software occlusion on its own was insufficient. Dan mentioned a designer-controlled, volume-based culling system we called player spaces in the context of streaming, but I thought of it in terms of rendering update frequency. Any occlusion-based culling system has to consider visibility every frame to do its job. In contrast, when a primitive is marked not visible, Unreal removes it from the scene, and all rendering work for that primitive is skipped until it is made visible again. Hence, volume-based visibility reduces the amount of work that has to be done every frame substantially. We even used this system in the previous game on PC because there were so many objects to cull that hardware occlusion queries were taking too long. Finally, I should mention that we used HLODs not just for faraway objects, but also for objects near the player, essentially as a non-destructive workflow for mesh merging. We made engine changes to allow custom clustering criteria based on vertex count and other factors. There was constant tension between memory concerns and draw call reduction, so we ended up cutting HLODs from some areas to stay under memory budgets. It was a 4-year journey to ship this game, with concentrated efforts to accelerate streaming, swap in mobile-friendly systems, and leverage tools both blunt and precise to trim our rendering costs. But the results were worth it. A big thanks goes out to the whole team that made this possible, and we hope to see your own open world games on the MetaQuest platform in the future. Thank you for your time.